Hi, my name is Giuseppe Pisano, and I'm here to present the work Arg-tuProlog, a tuProlog-based argumentation framework. The presentation will articulate in three sections. At first, I will present a global overview of the framework, focusing on the context and the motivation that lead us to build it. Then we'll go through a little demo, and in conclusion, we will focus on our plans for the future. We are witnessing a huge spreading of IT-related technologies, as this phenomenon apparently is not going to decrease or stop. An ever-growing number of IT devices generate every day a huge amount of data made available to further analysis aimed at knowledge extraction. This growth has been sustained by great advancements in data-driven, artificial intelligence-related technologies like machine learning or deep learning, for example. Anyway, their adoptions lead to a number of major problems in those systems, in the resulting systems, as the lack of transparency, analyzability, and comprehensibility. This context gives space to the adoption of technologies belonging to the symbolic sphere, logic in particular, of artificial intelligence in order to compensate for the lack of data-driven approaches. However, at the moment, although the great theoretic advancements in the field, the tools suitable to the scenario are not many. So we need to build a new category of tools possessing key features as reliability, flexibility, scalability, transparency, and others. So the key formalism that we choose for Arg-tuProlog is argumentation. The theories and tools belonging to this field offer a number of interesting features for modern intelligent systems. For example, the ability to deal with inconsistent or incomplete information, the high degree of transparency, the inherently interactive nature of argumentations. Frameworks and theories. In the context of multi-agent system, for example, such type of technologies could be very useful in order to facilitate agreement and contribute to the resolution of disputes. So, from the idea of building a modern tool with argumentation capabilities is born Arg-tuProlog. In syntax, it is a lightweight tuProlog-based tool for structured argumentation. It has been created with modularity and flexibilities as the two main principles. The entire framework is nothing else than a collection of tuProlog libraries, so this enables it to be easily customized, expanded, and used effortlessly in a high number of systems thanks to the JVM support. As for its features, let's discuss it with a little example. We model a case borrowed from the legal field of medical malpractice. We want to determine the liability of a doctor. A doctor is judged liable if he harmed somebody and if it has been determined that it was negligent. As for the syntax, we have facts modeled as rules with no premises and normal rules. Every rule possesses an identifier, a set of premises on the left of the arrow, and a conclusion on its right. It is possible to express strong negation through the dash notation. But let's continue on the tuProlog IDE. So this is the IDE shipped with tuProlog. It is fully compatible with the Arg-tuProlog framework. Moreover, the interface has also been extended in order to graphically visualize the result of the argumentation phase. The tool offers two distinct ways of functioning: the graph-based mode, providing as output the labeling of the entire argumentation graph according to the specified semantic, and a query-based mode. This mode provides as output the evaluation of a single query that is given as input according to the chosen semantic. As for the semantics, at the moment, Arg-tuProlog is shipped with three of them: grounded, burden of persuasion, and burden of persuasion complete. We have not the time to enter into the details of these semantics, but you can find all on the paper. Let's now apply them to our example. We will show only the graph maze mode. At first we only use the grounded semantics. As you can see, using grounded labeling, we obtain that almost all of the arguments remain decided. Then the side arguments are the gray circles on the graph. But now, if we enable the partial burden persuasion labeling on the absence of negligence of the doctor, we obtain that the argument for his negligence, that in the graph is A4, that argument becomes acceptable. This is caused by the missed satisfaction of the burden of persuasion constraint. If we enable the burden of persuasion semantic completion, then we can see how the result is a completely decided graph. This is because the consequences of the burden of persuasion are propagated to all the connected arguments. So now we can return to the presentation. So we have completed our small introduction to the Arg-tuProlog framework. Summing up, the tools has been built following all the guidelines regarding modern, well-engineered systems. Thanks to the JVM, it is suitable to be easily integrated in the vast majority of modern applications, bringing the possibility to correctly deal with inconsistent informations, integrate legal aspects, and offer an easy-to-use and transparent interface to the users. In the future, we plan primarily to expand our support to new argumentation semantics and enhance the global efficiency. Furthermore, we are completing the migration to the new version of tuProlog that has been recently completely rewritten in Kotlin. This will extend the support of the Arg-tuProlog framework also to JavaScript and web platforms. We want also to begin the investigation on the possible integration of symbolic technologies in the framework on the wave of the advancements in the neurosymbolic computation field. That's all. Thanks for listening, for your attention.
I'm Villadsen from the Technical University of Denmark, presenting tautology checkers in Isabelle and Haskell. Our goal is to have a formalized logic textbook, and we're using our tools in our automated reasoning course. There we are using the Isabelle proof assistant and automatically generate code in Haskell. We are considering here only propositional logic, but we have also worked on first order logic and higher order logic. For propositional logic, we call the provers just microprovers, and here the prover, when given the formula P and not P, should return false, and on P or not P, it should return true because it's a tautology. And we are going to show formalized proofs of termination, soundness, and completeness, so it's not hard to write a Haskell program working as a prover, but here we are on just one slide showing that we can also obtain proofs of termination, soundness, and completeness. In fact, we are in the paper considering 4 provers. First one are using falsity and implication, so their negation is defined as P implies bottom for falsity. We are then considering a prover based on negation and conjunction, then one on negation and disjunction, then kind of combining it all in a very short proof for the negation normal form. And there we only have propositional variables with negation or not with negation, and the only operators are conjunction and disjunction. So here is the entire Isabelle formalization with first the syntax, then the semantics, then the sequence calculus, and then we define the prover. We have a small example, we prove completeness and soundness, and then we generate code in Haskell. So I'll go through step by step. We first import the main library of Isabelle Hall, and then we define the formulas, and A is a type variable, so we don't specify the nature of the propositional variables, but we construct literals from either atoms or the negation of the atom. That depends on the bool. And then the operator, we are combining conjunction, disjunction in one. So if the bool is true, then it's a conjunction, otherwise it's a disjunction. This will be seen in the semantics. That's the function val, where in the second rule you can see that it's conjunction in case of the bool being true, otherwise it's disjunction. And for the atom, we simply look up the propositional variable in the environment I. Then the sequence calculus itself, so it's returning a pair of sets of propositional variables, and it's a sequence calculus and a one-sided one, so in case of the empty list, so we have the sequence as a list. In case of the empty list, we simply check whether there is a common element in the two sets of pair of list of sets of propositional variables. In the second line, you'll see that we collect the atoms either in the first element of the pair or in the second element of the pair, depending on the bool. And in the third line, for the operator, in case of conjunction, well, we do a double recursion. And in case of the disjunction, we split up the P and Q in front of the sequence. Then we have to show that these patterns are complete, and we also show termination by writing a measure based on the size of the formulas in the sequence. Then we define the prover itself as an abbreviation where we start with the empty sets in the pair in the first argument in the environment, and then just add P as the sole element of the list in the sequence. Here's a small example, and Isabelle will have this pop-up feature where it will evaluate this and we get true, and we can also notice that we can actually use a variable n for the propositional variables, so it's a bit more general than just executing on, say, a particular name for propositional variables. So that's an example, and then we obtain the main completeness result. It's also a soundness result, so cannot go into the details, but we establish for all environments and sequence that it's having the right semantics, and the proof is also by using the automation in Isabelle, the auto method. And then we can simply define the prover itself and the theorem about it, saying that it has to be true for all valuations, all interpretations. The value has to come out true, and that follows easily, and then we can generate the code in Haskell. And again, Isabelle will, if you click on theory exports, obtain the Haskell code that I will show on the next slide. So that's all needed for termination, soundness and completeness, and obtaining this Haskell program essentially with the example inserted at the end. Thanks.
Good morning everyone, I'm Francesco Fabiano, and today I'm going to present you my work in which I formalized the notion of trust for multi-agent epistemic reasoning. So this is just the presentation outline. First of all, we're going to introduce some basic notion of multi-agent epistemic planning. Then we're going to introduce some features of the epistemic action language MRL. After that, we're going to explore the contribution of the paper. Then we're going to conclude the presentation. So what does it mean, epistemic reasoning? Epistemic reasoning concerns all the reasoning that is not only about the state of the world, but also about the agent's knowledge or beliefs. These can be used to represent point of view, beliefs, knowledge relation, and so on and so forth. When epistemic reasoning is applied to the planning problem, we get multi-agent epistemic planning problem. This means that we want to find plans where the goals or formula in general can be referred to both the state of the world or agent's knowledge or beliefs. So to model these domains, we need an epistemic action language, and one of the most comprehensive one is MIRO, which was introduced as a modification of MI star, a language introduced by Barali and others in 2015. This language is able to reason on a limited nested belief and common belief, and introduces three types of action on text sensing and announcement. The first one is used by the agents to modify the word, while the last two are called epistemic action. Sensing is used by an agent to refine her knowledge about the word, while announcement is used to share information. Moreover, in this language, we have a concept called agent's awareness. So an agent can be, with respect to an action execution, fully observant when she knows everything about the action execution and about its effects, partially observant if she knows only about the action execution without knowing the effects of the action, or oblivious when she doesn't know anything about the action execution. Even though MIRO is a quite comprehensive epistemic language, still lacks of some concepts such as trust, misconception, or lies. These concepts are needed for a real-world scenario. For example, if you want to try to encode an economy or politics situation. That is why in this paper we focused on trying and formalize the concept of trust for multi-agent epistemic planning. To do so, we introduced two new announcements in MIRO. The first one is called untrustworthy announcement and formalize all the situation where the agent that doesn't trust the announcer will not change her point of view about the word, while the second one is called mistrustworthy announcement, and this action captures all the scenario where the agent that doesn't trust the announcer will believe the contrary of what has been announced. This second action has been introduced to try and formalize all the domain where there is one agent known to have a faulty perception of the word. Along with the new actions formalization, we also provide and demonstrate some desired properties that ensure the correct behavior of the new actions. Moreover, we also describe for MI star the new action without providing the desired properties formalization. Since we don't have enough time to discuss the transition function, if you're interested, you can look at it in the paper. We're going to try and explain what we have done through an example. So to do so, we're going to use the domain grapevine, where agents try to exchange secrets. So in this example, we have 5 agents. In the initial state that is depicted in the slide, we know that A, B, C are in room 1, D in room 2, and E in room 3. We also know that B and D trust A, while C and E do not. Moreover, we know that it's common knowledge that only A knows secret A. So, after executing an untrustworthy announcement where A announced secret A, the state you see in the slide represents the updated state. Considering that in the example, the announcement that A made was an untrustworthy announcement, we can extract now the belief from the updated E state represented here in the slide. So from the graph, we know that A and B know secret A because B trusted A. C believes what she believed before, so she doesn't know about the secret A, but she knows that A and B both know the secret of A. D, that is a partially observant, knows that A and B knows the value of secret A without actually knowing the value, and also knows that C didn't change her beliefs about the word. And E, finally, didn't change anything about her point of view because she's oblivious. So as already said, these represent the execution of untrustworthy announcement. The execution of mistrustworthy is quite similar. It only changes for the agent C that will know not secret A in the updated E state. Given the time constraint, I cannot present you the formal differences, but in the paper you can find properties about the execution of the action and the resulting state that are demonstrated and that guarantee the correct state update, and therefore we can actually use these two new actions to design new epistemic scenarios where trust is involved. So in conclusion, what we did in this work, we formalized two new actions for multi-agent epistemic planning that allow for trust to be inserted inside these domains. And also we demonstrated that these two actions guarantee a correct state update. The next step of this work is to implement these two new actions in EFP, a C++ planner, and in Plato, an ASP planner for multi-agent epistemic reasoning, to enhance the trust function to be not globally defined so that each agent can have his own point of view of the trust relations, and to formalize the concepts such as lies and misconception. Okay, the presentation is over. I will be happy to answer any question. Thank you for your attention.
Good morning. I have to present to you our contribution to this conference, which is called Towards a Declarative Approach to Object Comparison. The first concept I want to introduce is the equality concept. Use it every day when we reason if two entities are similar. Which characteristics make two entities similar to each other depends on the domain at hand. We call those properties the equality state of the entity. Regardless of the semantics, every equivalence relation must be reflexive, symmetrical, and transitive. Order is a related concept that determines how two objects differ. Every well-formed strict total order relation must follow some rules. Both concepts are intertwined. The issue here is that both concepts usually span multiple methods, and those methods must be consistent with each other, and it's up to the programmer to ensure such a consistency. Another issue is formal usages. Language based on simple dispatch uses a single object to determine what to execute. Let us say we have two classes, point and color point. Instances of point are equal when they share the same coordinates. Instance of color point must also share the color. Let us say that we have O1, which is an instance of point, and O2, which is an instance of color point. If we call this statement here, we get true because both points has the same coordinates. But if we call this statement right here, we get false because equals implementation of O2 checks for color and O1 doesn't have a color. So it's a violation of symmetry. There are some proposals to deal with this problem, but they are not without issues. Some of them require all comparable objects to be mutable, while others are not uniform enough when it comes to how to denote comparison semantics. Some, like the code generation wizards, do not even try to handle this symmetric problem and focus only on the implicit contract between those methods. But mostly important, they only deal with a single aspect of comparison, which is equality. They simply don't deal with order. Our proposal encodes comparison semantics into metadata. That metadata acts as a single source of truth, from which derive the code of all comparison-related operations, including order. That mitigates the inconsistencies between each operation. We used plotkin-style small-step operational semantics to formally describe our solution. Besides that, we also used Cardelli and Mitchell record calculus and also featherweight Java. We tried to describe our solution in a language-agnostic fashion. The simple example helps us to visualize how this materializes. So, every field that partakes the comparison semantics of an object is tagged with the comparable attribute annotation. While it's not shown, we could also specify the order on which the fields are evaluated by using a parameter on the comparable attribute annotation. Our proposal revolves around a new construct we call comparison record. It is like regular records that contain the values associated to fields of each operand. Comparison records can also store a special kind of value we call the unknown value. Its semantics is the same as unknown found in tree-valued logic. The actual computation has two phases. First, we build a record by introspecting the operands of the operation being computed. Then, we evaluate the record by using a specific algorithm based on the operation being computed. Now, we will informally describe this process in detail. To build a comparison record, we pass the operands to the build function. It collects all the fields that are part of their equality state. In our case, X, Y, and color. Then, the procedure fetches the values that are bound to each particular field on each operand. First, it collects the value that is bound to X, and then that is bound to Y. In the last field, things get a little more interesting. O1 doesn't have a color since it's an instance of point, so we assign the value unknown to it on the record. When we evaluate the resulting record, the X field passes, which is also the case with the UI field. However, when the color field is processed, we detect a discrepancy and find that O1 and O2 are different. But how does it fare if we change the order of the operands? In that case, we'll end up with the same set of fields since the union of sets is commutative. After building the record, we end up with a very similar comparison record. The only difference is the last field, which has the unknown value on the other slot. Nonetheless, the evaluation process arrives at the same outcome, so symmetry is maintained. The next natural step would be to build a prototype of our solution. That is actually done. We submit a sister paper that describes the prototype to the Brazilian Symposium of Programming Languages, and it got accepted. Another option is to formalize how cycles are handled. They are a problem because their presence could lead to stack overflows. We can also study how to create collections that prevent the inclusion of multiple items. Lastly, I would like to thank you for your time. Ciao.
Hello, and thank you for attending this session. I'm presenting joint work with Juliana Bose. We investigate the problem of finding good execution for parallel processes. So we have a list of concurrent processes, and for each process you have to find a trace describing which events are executed in each process, and each event has a duration. And according to that, you should try to find an execution which maximize the degree of exploitation of the computational amount that you have in your system. In order to do that, we will associate a numerical measure to each trace execution to pick the best one. We start from the notion of event structure, which is a mathematical notion representing the idea of concurrency, and it's basically just a pair of binary relation over a set of events. First, you have the relation of causality, which is a partial order between events, and just telling you the order of execution. So you have an event, and then you have a causality linking to the next event, and so on. And then you have a reflexive symmetric conflict relation telling you which pair of events are not compatible. The obvious property that conflict must obey is that it should be a should propagate along the causality. So of course, if two events are not compatible, then so are their descendants. The good thing about event structures is that they are straightforward to formally represent, and also they allow you to introduce derived notions easily. So concurrency, for example, is just the absence of relations between two events, and a configuration is a conflict-free downward closed set of events, where downward closed mean that if an event is in the configuration, then also its predecessors must be. And finally, a trace has a maximal configuration, and the notion of trace is the one that we focus on in this work. So we want to find traces, and we want to find good executions for them. First, we see an example of a simple event structure, 11 events, and the arrows denote causality. And then you have the symbol denoting conflict, placed only in the earliest pair of events. So you have E1 and E8 are in conflict, but it's implicit that also their descendants are in conflict. The contour lines describe the two traces. We focus on the left one and see examples of possible executions for the traces, for that trace, sorry. Now the idea is to introduce an SMT way of finding traces and good execution for them. So we start from the notion of configuration, which is straightforward in SMT. You just introduce xi, which is the configuration for the event structure I that you want to find, and you just require that it is conflict-free and it is downward closed. Note that GI here is the graph of immediate causality for the event structure. Then you can ask for a trace by just imposing that a trace is maximal, but the problem here is that you are quantifying over a set here, which gives you a higher order function, a higher order formula, which is not allowed in SMT. So what we did was to find an equivalent first order formulation for this formula and formally prove that this equivalence using the theorem prover Isabelle. Once we did that, we focus on the execution of traces. So of course the easiest possible execution is a linear one, which is always possible by the order extension principle, but of course it's not the best one if you want to exploit some parallelism in your computation. So how do we do better, and how do we define better? We start from SMT formulas describing a generic execution, not necessarily linear. This is done by describing the execution using SMT, which are functions telling you when an event starts and ends. And then you just impose an order morphism between SMT and G, which is your partial order causality. Once you do that, you can determine the last terminating node for each possible execution. And you just take the end time of that last node as a measure of how bad or how good the execution is. And this allows you to use the SMT solver to pick the best execution. So the last thing I wanted to discuss is the process that we have to pass from one SMT formulation to another. For example, before we saw an example where we took our pen and paper problem and rewrote it into an SMT suitable way. And this process of rewriting SMT code is quite common in our work, even for performance reasons, for example. So what we want to have is some verification that we don't lose correctness in the process. To do that, we use Isabelle definitions to generate SMT definitions and prove the equivalence of the latter Isabelle generated definitions with the definitions that we use inside SMT. And then we can use Isabelle SMT definitions to prove correctness. So for example, here we have a small theorem assuming basic requirements for P, and then you also have the P satisfy the true concurrency Isabelle property that we use to generate S&T code, and you prove that you cannot have any event starting before the end of any of its parents. That's basically it. Thank you.
Good morning, I'm Pietro Moggeri, and today I'm going to present a translation from set theoretic formulae involving membership constraint into purely Boolean formulae. During the last years, my co-authors and I conduct a study on the satisfiability problem for small fragment of set theory, IMED, to find those fragments which satisfiability test is polynomial. In particular, we focus on two theories: Boolean set theory, comprising the Boolean operators union, intersection, and set difference, alongside the equality relator, and membership set theory, comprising the membership relator. During this study, we developed two useful tools. The first of these tools is existential expressibility, through which we can remove symbols from a theory. For example, it is possible to remove all the intersection by replacing its literal x equal y intersection z with x equal y minus z. Another interesting example is that to remove unions by replacing each x equal y union z with the conjunction x minus y equal z minus y and y minus x equal x minus x. Using these and other similar results, we prove that BST is actually the conjunction of all literals involving only set difference, equality, and disequality, and this is a quite convenient result for future proofs involving BST formulae. To bridge BST and MST, we studied the expressibility in BST of the literal x belongs to y, and we find out that membership literals are actually non-existential expressible in BST. This as a consequence of the following lemma. Every satisfiable BST formula Phi admits a flat model, namely a model signed M such that for all pairs of variables x and y, signed mx does not belong to signed my. To better understand this lemma, follow the steps of this simple sketch of proof. First, get a model M for Phi and let the M be its domain. Then, find a set S in the von Neumann hierarchy such that S has the same cardinality of the M, and for each pair St of its element, rank of S is equal to the rank of T. Consider then any biaction f from the M into S, and finally define signed M as signed MV equal to the collection of Fs where S belongs to MV. It is immediate to see that signed M is a flat model and also quite simple to prove that it is a model for Phi. To obtain the expressibility result we are looking for, we resort to the other tool we developed, OF expressibility, which is a weaker form of expressibility than existential expressibility, but for what concerns the satisfiability problem can be used in the same ways, with the only difference that each usage of OF expressibility requires an OF time step. For example, the literal x is the empty set is ON expressible in the language that comprises only union, equality, and disequality, as shown in the slide. Finally, our main result is that any conjunction of membership literals is ON squared expressible in BST. In the slide, you can see the formula that translates any conjunction of membership literals to a conjunction of BST literals, which length is in fact quadratic. We introduced two new sets of variables, the signed and the tilde variables. The signed variables are meant to replace the singleton, so that signed x stands for the singleton of x, while the tilde variables are meant to guarantee that the membership relation is acyclic. As you can see, the formula is quite lengthy, so it is more easy to focus on a short example. In this slide, we have the translation formula for the conjunction x equal y minus z and z belongs to y. Notice how the literal z belongs to y is translated by the literals highlighted in red into signed z is a subset of y and tilde z is a strict subset of tilde y. This in complete accordance with the intended meaning of signed and tilde variables. Also, the implied relation Z does not belong to Z is translated into sin Z and Z are disjoint, as you can easily verify by the contrapositive of the highlighted literals. Finally, the implied relation Z belongs to X is translated similarly to Z belongs to Y into sin Z is a subset of X and tilde Z is a strict subset of tilde X, once again easily verifiable using the highlighted literals. Such translation properties that, as you can see, apply not only to explicit relations like Z belongs to Y, but also to implicit ones like Z belongs to X, are meant to emulate membership. For example, the unsatisfiable cycle X belongs to something that belongs to X would be translated into the unsatisfiable cycle tilde X is a strict subset of something that is a strict subset of tilde X. For future study, we are planning to use similar approaches to that we have just analyzed to find translation for other operators, like singleton, rank comparison, and cardinality comparison. We also aim to obtain a translation for equality literals from formulae involving only the Boolean operators and the membership relation, which will be a symmetric result to that just presented. Moreover, as we have seen, by using set difference, it is possible to imply both union and intersection. Thus, on a different line of research, we defined an algebra based on a difference operator, and we are trying to prove, using an approach similar to that of the Stone theorem, that such algebra is isomorphic to any algebra that uses sets as its elements and the set difference as its operator. That's all for now. Thank you for your virtual presence.
Good morning, everyone. It's Alessandro Gianola, and in this talk, I'm going to talk to you about the problem of computing uniform interpolants in a web, the theory of pure equality and functional symbols. And I'm going to present two algorithms that solve this problem based on a compact representation of the output. So let's start with some motivation. We are in the context of infinite state model checking, where sets of reachable states and transitions are represented symbolically. And a precise computation of this set requires a form of quantifier elimination. But the point is that usually quantifier elimination is not computationally tractable. That's why other methods for symbol elimination, like predicate abstraction, are preferred. And even if quite efficient, they approximate states, so the computation is not exact. Nevertheless, quantifier elimination has strict relation with uniform interpolants, studied by Deepak, for example, and becomes tractable in some significant cases like this one, the one of modeling, verifying data-aware processes, where there are theories for read-only data storage. And for example, a web is sufficient to formalize relational databases with key dependencies in this context. This is a very simple but informative example, the system of sets where states are quantifier-free formula, transitions are existential formulas where the existential variables are elements from a database. And in order to perform verification tasks like reachability, we compute preimages, but so the preimages are set of states of reachable states. But the point is that these preimages are not state formula, because they are not quantifier free because of these existential quantifiers. So they should be eliminated, and they can be eliminated, fortunately, by computing uniform interpolants. So this is a very interesting notion, and we will present it. And the main contribution is to provide two complementary algorithms for this purpose, which share common preprocessing part based on congruous closure. The first algorithm is Tableau-based, and the output is in disjunctive normal form, whereas the other one exploits the notion of conditional DAGs and provides a compact representation of the uniform interpolant, and the output is in compressed conjunctive normal form. Of course, we prove correctness, completeness, termination of the algorithms. So let's give the definition of uniform interpolant. So for a theory T and an existential formula existing phi, a quantifier-free formula psi is a T a uniform interpolant if psi belongs to this set, the set of all the formulae that are implied by phi, and psi implies, modulo T, all these formulae that are implied by phi. So T has the uniform interpolation if and only if every extension formula has a T uniform interpolant. And this uniform interpolant intuitively is the strongest formula implied by the initial formula. And in some sense, in psi, the variables here have been eliminated. So this is the pre-processing phase. We first columnize the variables so they're treated as constants. So we flatten the literals in the initial formula using congruous closure. And the main ingredient we use here is this notion of DAG, which provides a sort of acyclic definition of the y variables in terms of already defined y variables or the z variables. So the base case is the z variables. And intuitively, this delta provides explicit definition of the y in terms of z. And they are used for presenting formula in a compact form in order to avoid substitution, which would cause an exponential blow up. And the nice feature is that every initial formula can be rewritten to a DAG representation form, which are the kind of formula that are manipulated by our first algorithm, the tableau algorithm. And so the idea of this algorithm is to use a sort of Knut-Bendix completion, the simplification rules, and also there are other rules, but the role of the DAG is in the second rule, because whenever we find an explicit definition of the E variables, the one that should be eliminated, so it's equal to a term T, which has been already defined, the E variable becomes a Y variables, and this definition is added to the DAG. And also notice the splitting rule, which creates branches based on these equalities of E3 terms, and that's why we call it a tableau algorithm. The output is the disjunction of all the formula obtained in every branch. So for the other algorithm, we need this other definition of conditional DAG. Basically, given a subset of E variables, a conditional DAG is a set of conditional equations, intuitively conditional definition of E variables, where step by step more and more E symbols, E variables are considered, and they are used to produce this formula phi delta. And these formulae phi delta are used in the conditional algorithm. So we have 3 steps. The first one, we produce Horn clauses, then we saturate the set obtained using the rewriting rule involving these variables, and then we compute all phi delta for every conditional DAG, and the output is the conjunction of all possible phi delta for all delta built out of this set. So of course both algorithms terminate and produce the uniform interpolants, and the results are proved using arguments from model theory and term rewriting, and the trick is to build suitable model extensions somehow. And let's conclude by saying that we presented 2 complementary algorithms. The first one is similar in spirit to the use of equality interpolants in Nelson Open Framework, and the main merit of the second one is to show that a very light form of completion is sufficient, thus simplifying the algorithm from another paper from CADE 19. And both algorithms are simple and intuitive. So an implementation of both algorithms is still future work, and also we would like to characterize the classes that require a polynomial time for computation of uniform interpolants. Thank you so much for your attention.
Good morning, everyone. I'm Andrea Loreggia from the European University Institute, and this talk is about the paper A Ceteris Paribus Deontic Logic, which is a joint work with Emiliano Lorini and Giovanni Sartor. So artificial agents are used to automate tasks in many different scenarios. Nowadays, they are so pervasive and so fast that it's almost impossible for humans to monitor them in order to predict any illegal behavior. So a possible solution is to embed a mapping of the governance into these entities. This will allow to partially translate legal and ethical requirements into computable representation of legal knowledge and possibly reasoning about it. So the aim of this work is to model a certain kind of conditional and unconditional obligations and permissions based on the ceteris paribus semantics. Informally, they introduce a preference order among state of affairs. So take, for instance, two state of affairs, one in which an obligation is respected, and another one in which the same obligation is violated, all the rest being equal. So clearly, the state of affair in which the obligation is respected is preferable to the one in which it is violated. So these notions are formally described in deontic logic and employed to map legal, normative, and ethical concepts. Obligations are used to describe something which is mandatory, while permissions are used to describe something which is allowed. So in this work, we model formal semantics for deontic logic based on the concept of ceteris paribus preferences, which was introduced by von Wright. The basic idea is that semantics of obligations and permission can be captured by viewing obligation as strict ceteris paribus preferences and permissions as weak ceteris paribus preferences over the possible world. We show that this notion satisfies some intuitive properties, and at the same time, it does not encounter some problems and paradoxes described in literature. Moreover, we propose to adopt an existing preference framework from the artificial intelligence area of computational social choice in order to compactly represent such ceteris paribus preferences. This is useful because we enable the compact representation of the normative system. Or the compact representation framework that we adopt in this work is called the CP network. We define a modal language with standard Boolean operators and modal operators, which model obligations and permission, plus an operator that represents when a norm is universally true. So just a quick example to exemplify and clarify some of these notions. So let's suppose that for some security reasons, a municipality enacted the following rules. So cats are allowed with no restriction, while dogs are not allowed in a public area, but you can keep one or more dogs in your own property. There should be fences when there are dogs in the property. On the contrary, there should be no fences when there are no dogs. So this set of norms can be represented using our language in the following way. And more specifically, as you can see, the first one model the fact that cats are allowed, while the other one represent an obligation or a preference for not having dogs over a situation when you have a dog. And the last two represent conditional obligations for fences connected with the presence of dogs in a property. We propose to represent this kind of normative system using CP-net. So the formalism allows to describe conditional preferences over a set of variables in a compact way. So CP-net model influences among variables through dependency graph, represent these influences using a dependency graph, where each edge represents a dependence. So for instance, in the slide, you can see the edge between the variable X and the variable Y. Each node represents a feature or a variable. The edge between the variable X and the variable Y says that the preference order over the values of the variable X depend on the assignment of the variable Y. When a variable has no incoming edges, then it is called an independent variable. Thus, a compact representation induces a partial order over the outcomes, which are complete assignment over to the set of variables. And the partial order is exponential in the number of variables. So the CP-net related to the previous example is depicted in the slide. As you can see, the variable C that represents whether or not there are cats is an independent variable, as well as the variable D. While the variable F that is connected with the presence or not of fences depends on the variable D. So moreover, as you can see, permission introduce indifference over the values of a variable. So look, for instance, at the variable cat, the variable C, while obligation introduce strict orders over the values of a variable. So there are clear connection between the deontic logic that we are proposing and the conditional preference framework. And one of the main motivations to adopt a compact representation is that this allows to infer interesting properties of the normative system, such as, for instance, consistency, avoiding for the enumeration of all the possible words. So to conclude, in this work, we propose a new approach to deontic logic, which is based on the ceteris paribus preferences. The proposed logic avoids for some deontic paradoxes, but also provide an adequate conceptualizations of obligations and permissions. And moreover, we show a new connection with knowledge representation from the artificial agents area in order to compactly represent and reason over the set of norms. So thank you very much for your attention.
Good morning to everyone. I'm Gabriele Buriola, and I'm going to present our results about a decidable theory of differentiable function with convexities and concavities on real intervals. Our starting point is Haskell's theory of reals, which is the first-order theory built up from real numbers with usual operations and relations. Here we can see an example of a sentence of this theory about the property for the generic polynomial of third degree to have at least one rule. The main result, due to Haskell, is the decidability of this theory. Different extensions have been developed in the years, both in algebra and geometry. There are also some analytic extensions, and we will consider one of these, namely the RDF plus theory. There are anyway some limitations in Haskell's theory. In particular, we can't define integer number as a subset of R. Our RDF plus theory is an unquantified first-order theory about analytic properties of real functions. The idea is to enrich Haskell's real arithmetic by adding variables and relations about functions. We have two types of variables: numerical variables, which play the same role as in Haskell, and functional variables, which represent continuous real functions. We have also some constant symbols, which represent numbers 0 and 1, and the symbols plus, minus, infinity. From these, we can build up our terms by joining together numerical variables, functional variables, constant symbols. Then, we can define atomic formulas of our theory, which concern property of real function, such as being greater than another function, being increasing, being convex or concave. For almost all of these atomic formulas, the defined interval can be quite general, being a closed, open or semi-open interval, bounded or unbounded. Starting from these atomic formulas, we can define also other derived relators. The semantic reflects this idea of an analytic extension of Haskell's theory. While the interpretation of constant symbols and numerical variables is quite clear, for a functional variable, it is given by a real function with continuous derivative, defined all over R. Using common property of functions, derivatives, and operations, we can define an assignment also for terms. Even intervals have their interpretation, which is quite immediate. Through an assignment, we can define truth values, first for atomic formulas, then for all other formulas. Given a semantic, we can deal with the decision problem, which, since RDF plus is an unquantified theory, is not about truth, but about validity. Our goal is to establish if a formula of RDF plus is valid true under any assignment or not. In particular, since there is a sort of equivalence between validity and satisfiability, our algorithm will transform a formula phi of RDF plus into an equisatisfiable formula psi belonging to Haskell's elementary algebra. Then we can apply Tarski decision method as a satisfiability checker to this formula psi. Through this algorithm, we can prove the decidability of RDF plus theory. As we said, our algorithm, which is divided in 4 steps, transform a formula of RDF plus theory in an equisatisfiable one of Tarski's elementary algebra. In the first 2 steps of the algorithm, which are quite preliminary, we consider some particular cases related to open or semi-open intervals, and we remove all negative clauses. In the third step, we evaluate all functional variables over all domain variables, introducing new literals. Finally, in the first step, we can remove all literals containing functional variables. We can do this by replacing all analytic properties on functional variables with algebraic conditions on numerical variables, using, for example, the different quotient. To prove the correctness of the algorithm, we must prove the equisatisfiability between the first formula and the last one. We can do this by using canonical models made up through linear interpolation with exponential perturbation. Further extension of this theory can be considered. For example, admitting operations between not only numerical variables, but also functional variables, considering higher order derivatives, and finally, considering multivariable function or complex functions. In particular, we are already working on an extension with some difference between functional variables. To conclude, there are also applications mainly in automatic theory improving. In particular, RDF Plus, together with some of its ancestors, will be integrated in the proof checker at NANO. Thank you for the attention.
Good morning, everybody. My name is Mauro Ferrari, and I'm going to present a natural deduction calculus for Gödel-Dammet logic, which internalize some proof search control mechanism. This is a joint work with Camillo Fiorentini. As witnessed by its name, Gödel-Dammet logic has a long history. Technically, it is an intermediate logic that is a subclassical extension of intuitionistic propositional logic, and it is also known as logic of chains, LC, because it is semantically characterized by linearly ordered Kricke models. In recent years, there has been a renewed interest in the computational interpretation of LC, and there are some works refining the parallel interpretation proposed by Avron in 1991. All these works introduce some kind of natural deduction calculus for LC. But the main problem of this calculus is that in all this calculus, proof search is highly inefficient. Our aim is to define a natural deduction calculus prone to goal-oriented proof search, exploiting the ideas we used for intuitionistic propositional logic. The main characteristic of natural deduction is that each logical connective is defined by introduction rules and elimination rules. Introduction rules introduce compound formulas starting from simpler ones, while elimination rule deconstruct the information contained in a compound formula. In this context, we can define a calculus for LC by adding to the calculus for intuitionistic logic an elimination rule internalizing the linearity axiom characterizing the logic LC. Indeed, this rule is an instance of a disjunction elimination rule where the first premise has been crossed out since the linearity axiom is valid in LC. The naive proof search strategy for natural deduction consists in alternating two phases. We have an up expansion phase where we apply introduction rules bottom up to extract simpler subgoals from the original goal. And we have a down expansion phase where we apply elimination rules top-down to extract facts from the assumption. These two phases generate sets of partial derivation, and we can build a full derivation of the goal from the assumption if we can glue together some of this derivation of this partial derivation to get a full derivation. Well, this proof search strategy that was formalized in the intercalation calculus is highly inefficient and does not provide a clear characterization of the proof search space of the calculus. To overcome these problems, we add some structures to the calculus. This structure will be used to drive rule application and to reduce the proof search space. First of all, the rules of the calculus do not act on simple sequence, but on judgments. We have two kinds of judgment. We have down sequence and up sequence. Up sequence also have a label that I will discuss in the next slide. The role of these judgments is to drive the corresponding expansion phase. As an example, in an up expansion phase, we eagerly bottom-up decompose up sequence until we get a sequence with a prime formula in the right-hand side. When we get prime formulas, we enter a down expansion phase applying one of the rules for prime formulas. The role of the labels in up sequence is to prevent the application of some rule during the up expansion phase. In particular, the characteristic rule of LC can only be applied to unblocked sequence. Since the rule is non-deterministic, this restriction allows us to reduce the proof search space. Finally, we impose some restrictions on the application of the characteristic rule of ALC. First of all, the rule can be applied only when the formula D in the right-hand side of the sequence is a prime formula or a disjunction. Moreover, the formulas A and B introduced in the premises must come from a final set of formulas depending on the goal formula G, that is the formula that we want to prove. Since the application of this rule depends on the goal formula G, all the calculus depend on the formula G. This is why we call it NLC of G. In the paper, we sketch the proof of the completeness theorem, which say that G is valid in LC if in our calculus there is a derivation of the up sequence with the label U, having G in the right-hand side and with no assumptions. As future works, we plan to design a goal-oriented proof search strategy for our calculus, similar to the one we already developed for intuitionistic propositional logic. We also aim to investigate the relation of our calculus with those presented in the literature and to study the computational interpretation of NLC of G. Well, that's all, and thank you for your attention.
Hi, I am Elena Mastri, PhD student at University of Calabria, and this is a joint work with Jessica Zangari, Simona Perri, and Francesco Calimeri. The answer set programming is a well-known declarative paradigm used for knowledge representation and reasoning. Thanks to the availability of efficient SP systems and the possibility to easily represent complex computational problems, it is successfully employed in several contexts. Generally, the same computational problem can be represented through different but equivalent SP encodings. However, actual SP system performances strictly depends on the input program structures. Then, when performances are crucial, proper expert knowledge is needed in order to select the most efficient encoding for a given problem, going against the declarative nature of SP. For this reason, our goal is to automatically optimize the SP programs using rewriting techniques embedded within the SP systems. A possible rewriting split an SP rule into multiple smaller ones, preserving the semantic by exploiting the tree decomposition of hypergraph. In particular, this technique is based on the concept that a rule can be represented through an hypergraph, where each contained variable corresponds to a vertex of the hypergraph, while the literals forming the rule represent the hyperedge within this hypergraph. From this representation, we eventually may construct more than one tree decomposition, each of them intuitively representing a possible decomposition of the original rule. However, the application of this rewriting does not always lead to a performance improvement. Indeed, there exist cases in which maintaining the original rules may be preferable. For this reason, we need proper means to correctly estimate the impact of rule decomposition over the computational time. We have proposed a machine learning guided rewriting approach that automatically classifies rules as better to decompose, better to not decompose, or indifferent, obviously based on the previous observed effect of decomposition over the grounding time. So we designed, trained, and tested a predictive model. The devised features are 19 in total and involve several statistics on non-ground structural properties and domain information. In order to create our dataset, we collected all the composable rules coming from benchmark of the SP competitions and the QQBF domain. Given the ISP programs, we splitted them into subprograms containing a single decomposable rule. Then we used these subprograms to compute the features that related to the contained rules. Finally, in order to obtain our example set, we properly associated a class label to each computed feature set. This table reports the instances distribution among classes within the obtained dataset. We can see that it is highly unbalanced since most of instances belong to the indifferent class. As a convention, it has been divided into training set to extract the predictive model and into the test set to evaluate the extracted model. We designed the model using a multi-layer perception neural networks. These networks allow to learn complex relationships among data, and they are widely used in classification context. Since we are dealing with an highly unbalanced dataset, we adopted a cost-sensitive learning approach. In particular, implementing an alpha-balanced focal loss, we tried to guide the learning process to better classify instances belonging to the minority classes. The model has been trained for 3000 epochs, and its quality has been assessed through precision, recall, and F1 score, as well as the confusion matrix and the area under the ROC curve. This slide reports the results obtained by the model over the test set. In particular, the confusion matrix reports the model prediction distribution among classes, while the plot of the ROC curves summarizes the model capability to distinguish among classes. In particular, an area under the ROC curve very close to 1 means that the model is actually able to correctly understand whether to apply the decomposition or not. Finally, the table reports the detailed value of the used metrics. In order to make the model interact with the Levy system, we created a preprocessing module that acts as an intermediary between them. In particular, given an ISP program, the preprocessing module computes the feature set for each contained rule and calls the machine learning model in order to obtain the classifications. Then the model choices are attached to the SP program in form of IDLV annotation that will be properly interpreted by the system. We properly analyzed the impact of the proposed heuristic on the IDLV performances. In particular, we compared the presented IDLV induct with the well-assessed IDLV deduct version, which internally employed the deductive method to guide the decomposition process. The plot summarizes the results obtained by these versions over the fourth SP competition, and we can see that IDLV induct behave consistently with IDLV deduct. Indeed, if we focus to the last part of the plot, we can see that the trend of IDLV induct is almost similar to those of IDLV deduct. In conclusion, we can say that the proposed inductive heuristic correctly identifies whether it is convenient to apply the decomposition overall rule or not, obtaining results very similar to the well-assessed deductive method. As future works, we want to enrich the feature set used for the classification and to experiment with other machine learning algorithms, as well as expand the application of the inductive heuristic to other rewriting techniques. Thank you for the attention.
I'm Giuseppe Mazzotta. I will present you the paper compilation of aggregates in ISP. ISP stands for Answer Set Programming, and it is a well-known problem-solving formalism in computational logic that is based on stable model semantic. ISP is used in many real-world contexts, such as natural language processing, robotics, scheduling, and many others. In order to compute stable models of a particular ISP program, we need a particular system called the ISP solver that implements the ISP semantic. In particular, an ISP solver follows a ground and solve approach, in which there is a grounder module that computes the ground version of the input program by substituting all the variables in the program with all the constants in the program itself, and a solver module that takes as input the ground program and computes its stable models. In many cases, the size of the ground program can grow exponentially, fitting all the available memory, and then the solver cannot start the model computation. This problem is known as grounding bottleneck. However, different strategies have been proposed in order to reduce the effect of this problem. And among them, the most promising techniques are those techniques based on the compilation of problematic constraints into dedicated procedure used by the solver during model computation. In particular, we can follow two approaches. The lazy approach, in which the solver computes a candidate stable model of the simplified program, and if this candidate stable model is coherent also with missing constraints, then it is also a stable model of the original program. Or an eager approach, in which the solver computes a stable model of the simplified program, preventing conflicts with missing constraints. In order to do this, we need an ad hoc procedure called the propagator that makes inferences in order to prevent constraint failure. Recently, an implementation of the eager technique has been proposed. This implementation is built on top of the solver WASP and compiles constraint into the dedicated C++ procedure. However, this implementation is limited to constraints that do not contain aggregate functions. Aggregates are a very powerful construct that makes ISP effective in representing a complex problem. So, the objective of this work is extend the compilation to constraints that contain aggregate count. In order to do this, we implement an algorithm that takes as input an ISP constraint and compiles it into a dedicated C++ procedure that is automatically generated and matches the external interface of the solver WASP. In particular, this procedure implements the unit propagation for the aggregate count literal and is able to compute the reason that supports the unit propagation, and is able also to simulate the constraint instantiation in a very optimized way. In order to better understand the idea behind the propagation, let's suppose we have this the following ISP program. If we want to prevent the failure of the constraint, if A1 becomes true, then A2 and A3 must be false. At the same time, if A2 becomes true, then A1 and A3 must be false. Unfortunately, the propagator code is not so easy, but is not human readable, and it's very complex. An example of propagator code is reported in the figure on your right. The algorithm that we propose then produce the propagator code automatically, and it will be customized according to input constraints. The entire system has been tested and evaluated on art benchmarks from ISP competition. In particular, we select combined configuration and abstract talent frameworks that are encoding that contain constraints with aggregate count. In particular, performance of our approach was compared with the plain version of WASP, and the obtained result show that our approach takes a smaller execution time and increase the number of solved distance in both cases. In the future, then we plan to extend this benefit also to constraints that contain whatever kind of aggregates, for example, sum, and if it's possible also to rules and not just constraints. Thanks for the attention.